In this lecture, we will study the predictive control problem when the process model is described by state space equations. Now, recall that we have assumed that the control input will only change at times t plus 1 until t plus nu minus 1. Nu here, it is the control horizon. And the control input will remain constant after that. So that we have ut plus k is ut minus nu minus 1 when k is between nu and n2 minus 1. And here, N2 is a prediction horizon. We want to have the first step in MPC is to predict the output. We want how the predictions expressed in terms of delta t plus k conditional t rather than the control input ut plus k conditional t. Recall that the definition of delta t ut plus k conditional t is ut plus k conditional t minus ut plus k minus 1 conditional t. So therefore, we have the UTT. So UTT, so based on the definition, so UTT will be that UTT plus UT minus 1. So this is based on the definition when K is 0. When K is 0, then UTT is delta UTT plus UT minus 1. So on, we have UT plus 1T. It will be delta. So when K is 1, it will be delta T plus 1T plus U, when K is 1, it will be UTT. Then based on the first equation, we know UTT is delta UTT plus UT minus 1. So therefore, we have delta UT plus 1T plus delta UTT plus UT minus 1. Based on these two equations, I think so you can find out the patterns. So when the UT plus NU minus 1 condition T will be dot UT plus NU minus 1 condition T plus delta UT plus NU minus 2 until delta UTT plus UT minus 1. Now we have the future control input, UTT, UT plus 1, UT plus NU minus 1T, expressed in terms of delta UTT, delta UT plus 1T, delta UT plus NU minus 1T, and UT minus 1. is the last known control input. In state space models, to predict output, we need to first predict the states. Maybe let's assume we have unknown states. If the states are available, we can just use xt, suppose current times t. If the states are not available, we assume, so we have a prediction algorithm or state estimation algorithm can estimate so the current state. Let's use x height t to denote the estimate of the current state. Then we can use the state space equation to predict the next state, the xt plus 1. So therefore, the prediction of xt plus 1 condition on t, so based on the state space equation, will be axt. Here we assume we have unknown states, so therefore we use the notation hat to denote the estimate of xt if the state variables are not available. Then we have but. So based on the previous equation, we know that b utt will be dot utt plus ut minus 1. We have b dot utt plus ut minus 1. So therefore we have axt plus b dot utt plus but minus 1. So this is the equation to predict xt plus 1 at the current time t. Then let's do one more. So let's predict xt plus 2 at the current time t. So based on this equation, it will be xa xt plus 1 conditioned on t plus b ut plus 1 condition on t. Again, so based on the previous equations, we know the ut plus 1t will be delta ut plus 1t delta utt plus ut minus 1. So it will be the prediction of xt plus 1 condition on t. So based on this equation, it will be ax hat t plus b dot utt plus but minus 1. So this is xt plus 1 condition on t, then plus b times, so ut plus 1, so will be delta ut plus 1t plus delta utt plus ut minus 1. Then it will be, so here should be a square x hat t plus, so let's combine all the terms with that utt, so we have ab, that utt, we have b. We have ab plus b, that utt. So AB plus B should be A plus IB dot UTT. Then next we have UT plus 1 for ut plus 1, the only coefficient is b. Therefore, plus b dot ut plus 1t. Then for ut minus 1, we have a b ut minus 1 and b ut minus 1. So therefore, we have a plus I b ut minus 1. So the second equation for xt plus 2, prediction of xt plus 2 at time t will be a squared x hat t plus a plus I times b dot utt and b dot ut plus 1t and a plus I b ut minus 1. Now let's try to find the patterns. So as we can see, so the matrix, so the coefficient of x t hat, so will be a, depend on the order. If here is 1, it will be a power of 1. So here with 2, it will be a power of 2. In the general case, if xt plus k, so here will be a power of k. Then next we have is for the change of the control input, it starts with dot utt until dot ut plus 1t. So this one will be, so t plus 2 minus 1. So for example, if here's k, it will be from utt until ut plus k minus 1. So similar here, if we have ut plus 1, then it will be ut plus 1 minus 1 will be dot utt. It's like an increasing order for dot u t plus 1 until t plus k minus 1. Then for the coefficients, we always have a b here, we always have a b here. Then for the coefficients, it will be, so a plus I, then this a, it will be one order less than this a power of k. So if here is a power of 2, so here will be a. Then until, so a will be like a polynomial of this matrix A. So here will be a power of 1, here will be a power of 0. Then for this one, so here a starts with a power of 1. Then here we start with a power 0, this identity matrix. Then for the control input, it increases with the time. Then for the coefficients, it's a polynomial of A. It's a polynomial of A. Then it decreases, the degree of the polynomial decreases. Then here, so we have A here. So then it start, so this is a power of 1, then we have a power of 0, this is I, so b dot utt. Then for the coefficient ut minus 1, it has the same coefficients with dot utt. You can also see from here. So the coefficient ut minus 1, t, it will be a plus ib, it is same with dot utt. So therefore, we can say so that the ut minus 1, it has the same coefficient with dot utt. Then with this pattern, so we can get, okay, so the general case until xt plus nu minus 1. So xt plus nu minus 1. We know the power. So let's do this until xt plus nu. Here's nu. So based on this two equation, we know, so here will be a power of nu, here's t plus nu. So here will be nu, so x hat t. Then we start with a polynomial, okay? The control input will be dot UTT and plus something like dot UT plus 1T and continue until, so the one less than T plus NU to be until, so that dot U T plus NU minus 1T. So the control input increases by 1 starting from UTT. Then the coefficients, so it will be, so 1 degree less than the A power of NU, it will be A power of NU minus 1, and so on will be A NU minus 2 until I. So similarly for the U dot UT plus 1 will be, it starts from A, so NU minus 2 will be 1 degree less, and so on until I. So because this is the case, so when this T plus 1 and so the order of this A, so will be T plus NU minus 1, T plus NU minus 1. So similar for here, if we have 0, if we have T, we have NU minus 1. So the sum of the two will be T plus NU minus 1. Then we have the last one will be delta U T plus NU minus 1. So it will be corresponding to the A power of 0. So the last one will be B. Then we know the last one should be, so UT minus 1. So its coefficient will be same with delta UTT. So it'll be A NU minus 1. So A NU minus 2 and so on. Then we have I here. So this is the equation to predict xt plus nu conditional t. It will be a nu x hat t plus a nu minus 1 until I b, that's utt. So the last one will be b u t plus nu minus 1t. So it'll be, for the coefficients of ut minus 1 will be n a and u minus 1 until I. Then there'll be some changes at the time when k is greater than the t, when the k is greater than nu. So there'll be some changes for xt plus nu plus 1. We can still follow the same formula, for example. So we have, so the xt plus nu plus 1t. Then based on this, the general pattern, so we have A to be nu plus 1 x hat t. And the polynomial starts from, so 1 degree less, so it'll be nu until the I b dot utt to the last one. So will be, so the A, not the last one, sorry, so be B. I think we have the delta U T plus NU minus 1, because the sum of the two will be T plus NU plus 1. So we have the power is 1 here. Okay, the sum will be T plus NU. So here the power A is 1. And we have T plus NU minus 1. Sum will be T plus NU. And the next one will be, so the B dot u t plus nu and plus, so the last one will be ut minus 1. So ut minus 1 has the same coefficients with delta utt. So be a and u, so on until I. Then because you can see this is something like interesting. So that delta u t plus nu. So based on the definition will be, so the delta ut plus nu will be, so ut plus nu minus ut plus nu minus 1. So we know, so for ut plus nu, it has the same value with ut plus nu minus 1. So therefore, the delta ut nu condition on t will be 0. So therefore, this will be 0. Then the last term here, so will be delta, so a plus I, so b delta t plus nu minus 1. So all the following terms regarding the ut plus k, for k is greater or equal to nu, so will be 0. Okay, we have this formula here. Then pay attention to the coefficient of a here. Okay, so because this is nu plus 1, okay, this is nu plus 1, so here will be a power of 1. Then now let's try to get the general case until xt plus n2, xt plus n2. Okay, so we know this xt plus n2 plus 1 condition, t plus n2, sorry, just xt plus n2 condition t, so will be, so here the t plus n2, so for is a power of n2 x hat t. Then we have 1 degree less will be a n2 minus 1 and so on, plus a plus I will be delta utt and so on, okay, and so on, okay. Then the last one again will be b, so the last one b delta, so the last one will be, so the b delta ut plus nu minus 1 condition on t. Okay, let's try to find out the coefficient. Okay, so after that, so the delta ut plus nu, that ut plus nu plus 1 will be 0. And the last one will be but minus 1. We know it has the same coefficient with delta utt. Therefore, it will be a n2 minus 1 until a plus I. Okay? So let's try to find the coefficient here. So therefore, we can see, so we can write this t plus nu, so similar like that. Okay, so it'll be t, similar like this one, t plus nu plus n2 minus nu. Okay, t plus n2 minus nu. So if it's nu plus 1, so the here it starts with a power of 1. And now we have a t plus nu plus n2 minus nu, so it will be starts with a, so n2 minus nu and until I. Then, so this is our general formula here. So the only part we need to pay attention is this one. So the last one is e delta ut plus nu minus 1 condition on t. So then the coefficients of polynomial of A, it starts with n2 minus nu. Our next step is to write the prediction of the states in a matrix form. In matrix form, we have the xt plus 1 t, xt plus 2 t, xt plus nu t, xt plus nu plus 1 t, until xt plus n2 condition on t. We know for the x hat t, so it will be the power of a. It starts from a, then a squared, so the power of a, the same number with the k. So k is will be a power of k. So therefore, in this matrix form, we have a, so the degrees increase by 1, because t plus 1 to be a, so t plus nu will be a power of nu. So t plus nu plus 1 here will be a nu plus 1. For the last one, so t plus n2 here will be a power of n2. Then for ut minus 1, so ut minus 1, so it always has a b, then it is a polynomial. It's a polynomial of a. Then this degree of this polynomial will be 1 degree less than k, start with k minus 1. Then similar here, start with nu minus 1. Then here, start with so nu plus 1 starts with nu. If it's t plus n2, it will be a n2 minus 1. So therefore, for ut minus 1 start from b, then the sum of polynomial of a, we always have a b here, then its degree will be 1 degree less than the k. So here nu, so the highest degree of a will be nu minus 1. If it's here is nu plus 1, so here will be nu. This n2 here will be n2 minus 1. Then for the delta, so we have this b. So the first row will be starts b. The second row, we have, so the degree will be ab plus b. Then for the next one, it will be b. So here we have ab plus b, b and 0, 0. Then since for the delta utt, it has the same coefficient of ut minus 1. So therefore, we have the I from 0 and u minus 1 aib, then the degree of a is reduced by 1 until the last one b. Then for the k is greater than nu, so it will be something like this. Okay, again, here will be 1 degree less than this k. Then the last one, so the last one will not be b, it will be a plus I. So the a, this coefficient, this nu plus something, the nu plus something is the degree of a. So the last one will be, for this one will be ab plus b. So here will be ab plus b. That is same coefficient with ut minus 1. Here will be ab plus b for ut plus nu minus 1. So here is 1. So therefore, the last one will be a power is 1. Then for the n2, then the last one will be n2 minus nu. n2 minus nu. Then it has same, so 1 degree less than n2 for the first one. So here the change of the control input So we can also see at this point, if we write this in the matrix vector form, okay, write it in matrix vector form, then we can separate the prediction, okay, as the past information, okay, past information using the state estimate of the state estimate of the true state at time t and the past control input and all the future information, the change of control input. With this matrix vector form, we are ready to predict the output. Then we know, so yt plus 1t just c times xt plus 1t. So y2 plus 2t will be cxt plus 2t. Then yt plus n2t will be cxt plus n2t. So therefore, if we write this in vector form from yt plus 1t until yt plus n2t, it will be a block diagonal matrix with the c's in the diagonals, so multiplied by the states. So therefore, the predicted output can be written in this form. So let's call this y, then this is C matrix times this C matrix. So times, let's go back. The C matrix times this is called phi. So the C times this block C times this, it is called phi. The block C times this, it is called gamma. It's called gamma. And the block C times this, is called theta. Okay? So phi, gamma, and theta. So therefore, the predicted output in a vector form so can be written as, so phi, so the predicted state at the current time plus so gamma times the last control input plus theta u. So the u is the change, the delta ut plus nu minus 1t is a change of the control input. Now let's put the predict output into the object function. Let's also write this object function in a vector form. So this here, so we have the predicted. So here we have the predicted output. We try to minimize the predicted output with the reference trajectory. At the same time, we want to minimize the control effort. So the Q here is a block diagonal matrix from Q1, Q2 into Qn2. Then for the U, the delta U, so for the control horizon, from R1, R2 until RNU. So N2 is a prediction horizon. So NU is a control horizon. So if we write this in a vector form, so we write the norm as a vector multiplication, it will be so QU plus phi x hat plus gamma ut minus 1 minus W transpose, then the Q matrix, then the same thing, so QU plus phi x hat plus gamma ut minus 1 minus w plus u transpose ru. Then it can be written as the quadratic form. So u transpose phi transpose q theta plus ru, then plus the phi x hat plus, so 2 times phi x hat, so gamma ut minus 1 minus w transpose, so q theta u, q theta u. We know, so if we write this as half, so here we have 2 here, so this is h, so this is h. Then this is the B transpose. Then the equation we need to solve is the HU is equal to negative B. So therefore, then we can cancel the 2 here, So it will be B transpose Q C plus R this times U is equal to negative, so negative B will be is a B transpose, transpose have B transpose, so Q is symmetric. We have the inverse of this, so it'll be W minus phi x hat minus gamma ut minus 1. Then if we assume, so this C transpose Q C plus R is invertible, then we can find the optimal solution. Okay, we take the inverse of this, so U will be B transpose Q C plus R inverse, then Q C transpose Q, W the reference vector in vector form, minus 4, the state estimate, minus gamma times the last control input.